I'm talking in France and French and German, and I don't understand what you are talking in English or in Hindi. So that is the plan basically. So that's a good motivation, right? And the aim is within the next 1 month or two, we should have this thing done. It should not take. Actually, yesterday I showed a paper also, one of the paper which my undergraduate students has done in 1 month's time, in exactly 1 month time, and it is a published paper. Which group I was showing yesterday? Group A, which was math anxiety, right? Math anxiety. So that paper is published actually. So, and it's very good paper by the way. If you read that thing, although it is not expected from the undergraduate to write it in for the scientific journal, right? Okay, so definitely we have much more skills and we can do it much better level, basically, for sure. Okay, so T is there or not there?
Yes.
Okay, so let's take a break actually and we'll come back here. Is equally likely to get infected, and they are mixing also equally likely with others. So now what we will do is we will go and actually expand the horizon. So we will talk about epidemic model, epidemic, endemic. Can you give an example of what is epidemic and what is endemic?
It's within the region of
Okay, so that is
globally, endemic means it's almost it's eliminated.
Okay, give me an example of a disease in both the categories. Which is an example of an epidemic disease?
COVID was outbreak.
Okay. Flu is epidemic, endemic. Flu. Influenza. You get common cold, right? Common cold every winters or you get cold, and then you recover from it. And then next seasons happen next year, then you get again cold and recover from it. So that's an epidemic, short burst and dies out, right? Single outbreak. Endemic disease, what is an example?
Malaria.
Huh?
Malaria maybe.
Malaria. Why is it endemic? Cholera also.
Zika virus. I don't know. Zika virus is also.
Zika is in the selected regions.
Yeah.
Say it again.
It's almost like elimination stage, but
No, not necessarily. It has nothing to do with elimination. It has to do with endemicity. That means it is sustaining at a certain low level continuously for a long period of time. That is endemic. You know, in mathematics, you calculate endemic state, which is a steady state at a low level, basically. That's an endemic state. So, malaria, leishmaniasis, all these diseases, long-term disease, HIV is also becoming endemic now, right? These are not epidemic anymore. COVID was epidemic and it died, literally. I mean, let me rephrase it. COVID is still there, but it's not the same strain as the other ones, the one which has already passed. They have died. These are new strains for which, so although it looks overlapping, but it is different strain. Okay, so that's the difference. So the question is, if I want to capture something peak and dive, we already know SIR model, right? What if we want to capture and then sustain endemic situation? What do we do that?
We introduce periodicity.
Say it again?
We introduce periodicity.
Well, if there is a periodicity, but not necessarily you could have a periodicity, you could settle down at a very small level of disturbance, may not be periodic, right? So, you basically simply capture birth and death. Birth and death brings the endemic damped oscillations. When you simulate it, it is a damped oscillation, damp. It's damping and reaching to the steady state. Quite intuitive. So it is epidemic, short outbreak, no replacement of susceptibles, right? And that's, we already know this model, right? There is no birth and death here. There is no birth and death. ds by dt is equal to infection, comma di by dt plus infection minus gamma I, and gamma is the recovery, and there is no birth and death, right? And we already seen that thing, right? Endemic is there is a birth and there is a death in each compartment. Birth will always happen susceptible. That means everyone is born susceptible, right? And death will occur in each of the compartments. So death is here, mu is a death here, mu is a death. Okay? So birth and death is there, and therefore there are two equilibrium here. One is N00 and the other one is non-zero, non-zero. I compartment non-zero. S compartment, I compartment, R compartment. So there are two equilibrium. One is disease-free equilibrium and one is called endemic equilibrium. And this disease is referred as, this model is referred as endemic models. Okay, and they are used for long-term persistent behavior. If you want to understand how is malaria behaving, then I will use this model. But if I want to understand flu, I will use this model. You see the distinction in the models that one will use here. Then comes, so this is again endemic model only, and it's just a simulation of this model. Basically, it's a three-dimensional. There's no time component, first of all. This is infective, susceptible, recovered, and this is the initial condition. And you start with the initial condition, and it is in this three-dimensional plane. It looks like and going to the endemic state in the middle. Is an endemic state in the dark in the middle. So it's kind of coiling and going there. Now, if you see in the time dependent, this is a time. Same model. Both model is, both the simulation is for the same model, right? This is an endemic model because birth and death are there, right? Mu is there. Mu is birth and death. Birth is occurring at the same rate as the death rate, so that the population remains constant. People who are getting born at the same rate as people are dying. That's an assumption we are making to make things simple. So again, this is a SI model. So this is a time, and if you see, it's a damping happening, damping to a steady state, to endemic stage, right? So that is, and this is what you call it as a phase plane, and this is an S and I plane. So this is a phase plane here. Right? These are the terminology we use, and this is called as the temporal dynamics over time, because time is this axis here. Okay, so, and you can cross-sectional these things in either one of the scale. Either you want to capture I over time or S over time. This is S over time, and this is I over time. No, this is a S over time, sorry, this is S over time. The one on the screen. I don't know if you can see that.
Yes.
Okay. So this was about endemic, and then comes, now the question is this. Now remember so this is something is important. This type of model that I want to use depends on what is observed in the field. What does the disease look like? So these are three examples: HIV, malaria, and polio. This is the actual data from the field, case count. How differently they are behaving, the shapes of it, right? So you can't just use SIR model, the first model that I showed you, everywhere. It's not possible. It will not capture the actual dynamics that you are seeing it. So you have to first observe the data, and you have to decide on what aspects of the structure I want to incorporate in the model. I just showed you one structure, endemic and epidemic. There are other structures, and that's what I am going to now. So what is the difference you are seeing here? This is I, by the way, this is I. This is I. I is this is showing endemic state, literally an endemic state. HIV is close to an endemic now. It's not anymore epidemic. It used to be an epidemic at the starting stage, but now it is like an endemic. What is this one? Malaria. It has a cycle, right? What is this? It's a single outbreak, large, and almost died, right? So different models are needed. Here I need a model which can do this type of fluctuations, right? Here the endemic model might work, and actually you incorporate birth and death in it, and it captures very well this signal. Okay, so what you are seeing here is a damped oscillation, damping, right? So suppose if I want to capture how disease is oscillating in next few years, and it has not yet reached to the steady state, literally, I want to know what is the, in what cycle this is oscillating. I can compute, do some mathematics and compute the fluctuation cycle that is occurring here, and that is we do it at the very small scale, and we can compute time of that cycle, and the time at what time it is oscillating, and amplitude. So this is an amplitude, and this is the time in which one cycle occurs. Okay, this is just simple maths that one could work on and find out what is the oscillations look like. What is the period of an oscillation? What is an amplitude of an oscillation? You can compute mathematically. Now, I'm not going into the mathematics right now, but I want to tell you these things are there, right? So, mathematics is not difficult, but at least you should know. When you will know it, you will apply it and find it out the solution. And this happens in endemic, SIR endemic model, the same model that this damped oscillation, right? Damping means the amplitude is getting reduced over time, right? Now, if I want to incorporate the, I was saying malaria is a cycle, right? Why was it a cycle, by the way? Seasons. And season, how is the disease linked with the season?
It happens during the monsoon period in India.
It's a mosquito war, right? Mosquito forces the oscillations to exist in that disease, right? Because that's a mode of transmission. The transmission cycle of a pathogen is incomplete until unless mosquito come into picture, right? Half cycle of the pathogen is in the mosquitoes, another half is in the mammalian host, primarily human host. Actually, it has cattle also sometimes a preference for it. Okay, so you get malaria is a cycle, right? So how do you generate cycle in the model? Typically, say it again? Sine cosine function, right? That's the one. Because naturally there is nothing in this model that can generate oscillation. There is nothing else. There is no way you can generate an oscillation by itself until unless you force this beta to be some cosine sine function. And this beta is same as this beta, and now it is time dependent and it is oscillating. But the question is, what is the cycle of this oscillation, right? And that is estimated, the beta 1 and beta naught is estimated from the data. Does that make sense? And that's how we capture. Now, another feature of this is, once you put this thing and you estimate beta, you can get double cycle, triple cycle also. You see, as you are changing the value, this is a mu, birth and death mu parameter. As you are changing the mu from mu, this value, to this value, you can see the cycles are increasing. There are two cycles. There's occurring in that. So that's the beauty of this model. That simple model is generating very complex dynamics of oscillations. Okay. But this much of analysis one needs to understand because you think, oh, I cannot generate this. Suppose the disease look like this. If the disease actual data looks like this, you will think, oh, this cosine sine function will only do like this, not like that. But it is the same model can generate something like this. Does that make sense?
Yes.
So you will see the real data, and then you should know the behavior of certain simple models. Then only you can basically use it further for your work. Then comes another type of structure. We were talking about malaria, right? Now malaria is the two population models now. It's a human models and the vector model. Vector is a mosquito one. So this is a movie actually, and I think okay. So somehow the movie is not working. So basically, let me see how is it? Why is it not working? Okay, I will not able to do it right now. But there is a movie which shows the life cycle of malaria. So now what you are seeing is, you see in the previous model, the nonlinearity IS was due to this plus this cosine function, right? That was the nonlinearity. But now the nonlinearity is changed. Basically, this is S, but this is basically vectors are not infecting, and there is some complex things here, which is M is a proportion of mosquitoes, and the N is a population of humans. So it's a ratio. How many mosquito per person?
True.
It is capturing how many mosquito per person is in that region where the infection is spreading. And it has a biting rate. A and B is one is a biting rate. What is it? A is a biting rate, and B is a biting not always results in a transmission. There is a chance that a biting will result in a transmission. So this model can become very, very complex just because of this nonlinearity. Why? Because mosquito not only bite humans. Why do mosquito bite humans, by the way? Not you. Why do mosquito bite humans? We have to understand the biology, otherwise we are not justifying our model. We have to, if we are working on environmental model, we have to understand that just like environmental scientists. If we are working on vector-borne model, we have to just understand by entomologists. Entomologists work in insects. Right? So why do mosquito bite human? If we don't understand this thing, we cannot do justifiable analysis to the vector-borne model. Why do mosquito bite human? For fun? They kill us and therefore we will torture them. That's what it is. Right? Okay, what is it, Yogesh?
Sir, not in case of even mosquitoes, but most of these species which bite and slug, which bite humans. Basically, mosquitoes feeds on fruits and leaves. They suck the things out of them. But when female is in egg-laying stage, they require human blood at death by the body.
Okay, so there's two things he is telling. Very good point. Thank you for reminding. I didn't have this point. So first of all, only females bite. I mean, males also bite. But
Sir, I have one point to say. Actually, I had this discussion before with somebody else, and I had the same idea that only female bites and suck the blood.
no, that is not true. Actually.
Yeah. So Yeah.
I take my word back.
Yeah, yeah.
Yeah.
Yes, sir.
But there's more chances of female
Yes,
biting
that's
than
true.
male,
That's
but both bite.
Yeah.
They are not human blood is not a primary source of food. Primary source of food is other nectar, for
Yes.
example,
Yeah, true.
right? So the primary food is not that, but the biting occurs because usually during the time of laying eggs, females laying eggs. Human warm bloods helps in development of their eggs, and that's the why they do it. Okay, so in fact, there is a disease called as Chagas disease. You will be surprised how the disease transmission happens in that. You can't even think about, until unless you have read it somewhere, that how the transmission occurs. So Chagas disease is a disease that happens in Latin America quite a lot. Latin America is a South America. And so this bugs bites, and the symptoms is not many symptoms, normal flu-like symptoms, so people don't worry. And all of a sudden, after 1 or 2 years, a person has a heart attack. All of a sudden, and person dies. So it's a very deadly disease, very bad disease. But let me talk about transmission. You know, these bugs are called kissing bugs. And they are, when a person sleeps, they crawl the roof, go on the top, and then fall from there on the human host. Look at the amount of effort from evolutionary biology perspective this person is doing, this bug is doing. Falls on it, and then bites, but bite is not causing the infection. They defecate at the same time. You know what is defecate?
Yes.
They poop. Right? They take the blood and then they poop at the same time, and then the person rubs it, and that poop goes inside the wound, bite wound, and that's how the infection goes into the. Look at the nature, how complex it is. And these mechanism is modeled in the SIR type model. Otherwise, you will not be able to capture the true transmission rate of the bug. It's called Chagas disease. And the scientific name of the parasite is called Trypanosoma cruzi. Okay. So there, and I work in this area, so my role is this terms, to capturing it in a very complex way, because there are a lot of biology is involved, nature is involved in that process. Okay, so let me not waste more time in this. I have many stories to tell and it will take more time. So you know, in this malaria model, very simple to, so this is X is infected humans and Y is infected mosquitoes, and this infected are dealing with it. You don't really need a susceptible, because 1 minus of X is susceptible, because X is a proportion of infected and 1 minus X is a susceptible, right? Of humans, sorry. And then 1 minus yeah, 1 minus Y is fine. Yeah. So susceptible. These are susceptible mosquitoes, and these are susceptible humans, right? Okay. So that's a very simple model, and this was done by Ronald Ross at McDonald, and Ronald Ross got a Nobel Prize for discovering the malaria life cycle, and immediately after it, he has some models like this one. So very old, a century-old model. Now in this model, the reproduction number is square. When you calculate it by the same method, the method we saw it in the first day, you get a square. And why do you get a square? Why do you get a square?
Interest should be positive.
Say it again?
It should be positive number.
Intra-species, what does that mean?
Interspecific competition, actually it will happen in predator-prey model. Each species will grow more and it will compete with each other, like in square.
Okay. I mean, maybe you are explaining in technical term, which I am not understanding. Tell me in a simple way. So there is a mosquito, there is a human, this mosquito infect human, Human infect the mosquito, and then mosquito infects some other humans. So there's a two-step process, and that's what is happening here, basically. And it's a geometric mean. Square root is a geometric mean. Average of this and average of that. And that, I mean, not is geometric means is number here, and then square root, and that is what you will get it. And these are the product of those two numbers. Okay, so anyway, so this is a reproduction number of malaria. It's a two-step process, and therefore it happens. Next is age structure. Why do we need age structure model? And I will come on to this. Looks very complex. It's a PD now. Actually, it's a what type of equation is this? Integral differential equation, right? So it's a PD, which is partially derivative here, T and A, and then there is integration here. So it's a okay. So who can explain what it? Anyway, before I go into these equations and models, where do we need such models? No, don't go on the maths. See, you have to understand one thing. I think I was discussing the same few minutes back. My intention here is to change your mind, to pollute your mind in some sense. This is a line. Think about this as a line. Theoretical mathematician or pure mathematician is on this end. A clinician, a physician is on this end. You have to decide your trajectory of your life depending on where you want to stand in this line. You could be very corner of that, you will not know things on this side, or you could be close to this. You are already getting training of PhD here in this, but this is very difficult to come to this close to this. And my goal in this course, and Dr. Tripathi's goal is for you to shift your focus to come towards this side. And and it is very common that you will go back to your institution, you will go quickly back to that steady state. I mean, right? So you have to force yourself to think this way. I'm kind of making you realize this thing, and it is not easy to do that because it's a human nature to be in your comfort zone. And that's your comfort. My comfort is mathematics, right? So you have to push yourself a little bit to be, if you really want to. People who are doing a good job in infectious disease models are not mathematicians. Let me tell you this very clearly. One of the top-notch epidemic modeler currently is Dr. Gautam Menon in India, and he is in a biophysical department. He's not a mathematician. And he's doing amazing work. He's helping Indian policies to be very solid wherever he's called. He's not called everywhere because he's very sincere person, very ethical person, and he doesn't want to diverge. If you want to ask him to change his studies, he will not do that, which is a different issue. But he is an amazing researcher, according to me. And I don't know many researchers like him. There's another person, who was the one from ISC Bangalore? Skipping the name. He worked in cancer, actually, oncology now.
Sir, I'm also forgetting.
Yeah, find me the name very quickly in the Google. He's in a biomedical department or something like that. Okay, so these two are the folks that are true scientists, according to me. There are very few scientists that I will call that understand their own field, but also can do a policy decisions at a very high level. Their work is published in Nature, Lancet, PLOS ONE. And when you read their work, and they are editor actually of Times of India. I have just read his paper, Gautam Menon's paper, news on TB, tuberculosis, why TB is not under control, and he's writing an article for Times of India. What's his name?
Sir, I'm searching the name, but about Gautam Menon, sir, sorry to interrupt you. During COVID-19 time, he was really popular because I think he shifted to epidemiology at that time, and many media outlets even.
Yeah, I don't know whether he was popular or not, because there was other people popular, which I'm not sure. I know the background history there, and so.
Mohit Joli, Dr. Mohit Joli.
Yeah, so, and I don't agree with that, and I am from IIT Kanpur, so I know. He's saying that IIT Kanpur developed the model, but I don't agree with that model.
Government adopted that.
I know, that's the politics. That's the politics, that's a different.
Other guy, maybe Dr. Mohit Joli, you were talking about.
Dr. Mohit Joli,
Yeah.
from ISC Bangalore.
Yeah.
He is, actually the reason he is also pioneer at a very young age, he's just an assistant professor, he's my collaborator also, long time back, but he graduated from US,
Yeah,
Rice
yeah.
University,
Yes.
and then he moved to
From Rice.
India, basically. And so he is amazing if you want to work in an oncology field, cancer related field, and he does a lot of modeling work. So coming back to that, where is the age structure is needed? Where is the age structure is needed? Why is age structure needed? I mean, just because I want to do good maths?
To connect with reality.
Maybe
And what is that reality? Exactly. But what is that reality? That is what I am asking.
some disease may be specific for some age group or something.
Give me an example. That is what I am saying.
What is it? Alzheimer's.
Alzheimer is known to be old age.
Old age.
Yeah. Okay, but that's an age group is fixed. I mean, Alzheimer doesn't
Maybe a
happen.
disease have impact in different age groups or something.
Okay,
During COVID,
give me an example.
during COVID in India, some strains were affecting severely the old age,
Good
some
point.
age, and some have immunity towards that.
Yeah.
to one age
So
group.
he has a point here. So some strains were in the COVID were impacting young age more, and maybe older, but not in the middle age group.
Child-
That's a very appropriate for this thing. So we will need just 3 age group if that is the case. The lower group which is impacting, the upper age group that is impacting, and the middle age group because that's a less impact.
Maybe all the sexual diseases also we can see.
They are infectious,
Yeah.
but they
Well-
are not affected. Sometimes it becomes complex because those who are not getting affected severely, they are infectious, they are spreading, but they have immunity towards that.
Correct, correct.
And they are spreading towards the low, younger
Correct.
child and old age. in the
Correct.
family.
Correct. So he's right here. And what were you saying? Sorry, I didn't miss you.
Sexually transmission diseases,
Yeah.
children are less vulnerable or something.
Well, they are not in the cycle. They are not in the sexual stage,
Yeah,
right?
Yeah.
So that's a different issue,
Okay.
right? So, but if they are in sexual stage age group and they are not participating in the infection process, then it makes sense, right? So, okay, so that's where this age structure is important, because what happens is age plays a role in transmission process, and that is what you guys are giving an example. As people in a different age group have the different transmission rates, right? And it may not be a constant, like in the simple SIR model we were taking same beta for everyone in the population. But here the beta is this, which is dependent on age of who's giving the infection and also the age of who's receiving the infection. Right? So that has high, and again, these are the things that can become complicated in the model, and this is a discrete version of this continuous model. This is a discrete version. So it is showing 1, 2, 3, 4 age group. SIR model in first age group, SIR model in second age group, and third age group and fourth age group, which is equivalent to that. This is a continuous version of the age group. And again, analysis becomes very complicated, but still you can do it. Find the endemic state, find trivial state, and you can do some analysis in that, right? But as you add variables, it becomes PD, it is not easy. Now, also, Dr. Tripathi was talking about this Navier-Stokes equations and the boundary conditions. Do you think they do maths? It's very difficult. Until unless they linearized it, they reduce the dimension to linear system, and then you can do some existence uniqueness. Otherwise, you end up using simulations for the big model. And for simulations, they are very hardcore in the numerical methods, which methods to use. So you see, there is a challenge. Complexity, we like it, but we would not be able to do much math. Math becomes very limited, and so we have to reduce the dimensions and scale it down to do some analysis on that. Okay, so let's go to further. So this is another model which is infection age, and the infectious age model. This was what? This was because basically they were dying also with the age, because mu was the age, and you have to also. There is no birth term here. Where is the birth term? Where is the birth term here? Susceptible people are because they are dying here. Your mu is there. Mu is at death. But there is no, this is all minus term. There is no birth term. Where is the birth term? Birth term is here. This is the birth. Sorry. This is the birth. 80. This is the birth. At time 0, age 0, at all times, this is the birth is occurring. You see that? So birth is not coming here. So it's a logically you have to build these models, and appropriately you have to define condition. And what is it saying? That all age group people are giving birth. This is the birth rate, and all age group people are giving birth, and that is total birth at age 0. Right? I mean, all age group, not the kids, but any age after certain age will likely to give the birth, right? And that is what it is saying. And it's a homogeneous model, so I mean, there is not separating by gender, or so it doesn't have that model. But if you have an HIV model, that will have S1, S male, S female, I male, I female, R male, R female, and that's how we will model. And then this transmission term will be more complex there in that case. Okay, so this is age of infection. So, you know, sometimes you have the data on an age of infection. So as people age with the infection, age of infection, not age of a human. The previous one was age of a human. This A stands for age of a human. This A is not the same age. Where is the age? Sorry. Here. I'm representing it by tau. Tau is the one which is this. So age of infection is tau. Right? Because you have seen that in the flu, for example, you don't get infected right away. You get infected after a week. You are more sneezing and you are more coughing, and that's how the infection is spreading. But first 3 days you have tingling, you have like no sensation, but you will not be infectious during that time, right? So it depends on how old you are in age, in the infection, that you are getting more infectious. Now when do you use this model? When you have the data of that from the hospitals, if they have captured you know, how the pathogens comes out of the person as they grow next day. Do you understand what I'm saying? Then you will use this model, otherwise there is no use of this model. If you don't have the data of age of infection, there is no point in using this model. Just for doing fancy work, okay, fine. But there is not. And so what I am guiding you is not to look for a complex model to do the mathematical analysis, but for your research question and your data to drive what model to choose. Make sense? Yes, no?
Yes.
Okay. Or you guys are bored? I can stop. No. Continue? Okay. So this is what is age of infection here, and it's also, what type of equation is this? So it has integral differential equations. And also note, the partial derivative is only in the I. S is a total derivative. Because S is, I don't care about, there's no infection in S, right? There's no infection in R. Only infection is in I. And I'm talking about age of infection. So I is the one. Then come spatially structured, that is what you guys were mentioning. The models, there are different models here. One model is called meta-population models. Basically, meta-population, meta means multiple, and meta-population means multiple population. So you have a population in this city, population in this city, population in this city, and they are moving back and forth in different cities. And while you are moving, they are infecting in different places. So how do you model it? And so the lambda term is actually a function of how many goes out, infected people, how many comes in, infected people. Does that make sense? So it's this is a population, this is a population, and the people, in fact, both susceptible are also moving and infected people also. Now the question is, how do you model? There are two different ways you can model this thing. Think about that. If it is a long-term movement, that means people go and stay there. Maybe going, that's a one way of movement. Another type of movement is you go, spend some time, and then come back. So if you go from here and stay here, then this, your tag, if this is called as a population A and this is called as a population B, then tag here is infected person in A. When it goes here, it becomes infected person of B. But if it is a small amount of time it is spending, then it is still be considered as tagged as A. You understand my point? It's the only thing which will go in the infection process, the time it is spending in this population. Does that make sense?
Yes.
These are two different way of modeling it. And what is that two terms called as? Can you find it out online, please, both of you? It is, I'm forgetting what is the name of it. Ask meta population, two types of models, two different types of models. See, there's a name for it. I'm forgetting the name of it right now, which is very common name. If something doesn't come to your mind, that's it's irritating, right? Sometimes. So, okay. Another way is. So this is, what type of equation is this? I said two types of model, right? In these two types of model, it's a discrete structure. This population is one structure, this population is one structure. It's a discrete population, they are not linked, right? And so these are called as, these are differential equation models, or total differential equation models. And these are connected. SIR model for this patch, SIR model for this patch, SIR model for this patch, and they are connected. Right, but they are differential equation, not PDs, not integral differential equation. So these are differential equation connected by the rate in which people are moving or time they are spending in this. Okay.
At vertices there is network, and at vertices we have set up differential.
Correct. Okay, another type of model of this population mixing is called reaction diffusion equations. Reaction diffusion is you diffuse and then react. React is infection. Diffuse, you move, and you and this is PD, by the way, partial differential equation. Okay, So that is what I am talking about here. If a spatial dimension is continuous, this is a discrete dimensions. If a spatial dimension is continuous, if the population is homogeneous, then I want to capture the movement of the people, then it is a reaction diffusion models that we use. Okay, and so that's this thing. So this is spatial structured model. 3 models I have talked about. One which is capturing time, one which is capturing transition, long-term transition, and the one which is and reaction diffusion is for small distance movement, not a long distance movement, small distance movement. It's a diffusion. So, okay. So the question comes: how complex should a model be? What is your point here? What do you think? A model should only be complex as needed, depending on the question of interest, not because of the mathematics I want. Yeah. So that is the goal. That should be the goal. So your research question. You see, for last 3 days, I am forcing you guys, think about your research question, think about research question. Some of you folks might say, oh, why don't we use this differential equation or that differential, this complex mathematical structure. But I said, no, think about objectives. Think about research question. So that is guiding you, and that's the step of learning for you all to think about how modeling is supposed to be thought. And if you ask Dr. Menon or what is that name? I forgot again. Mohit Joli, they will do the same thing. They do exactly the same. In fact, they do run an experiment in their labs at Ashoka University and ISC Bangalore. Yes.
Sir, I guess the 2 terms you were saying that we have discussed before, Eulerian and Lagrangian approach.
Eulerian and Lagrangian approaches. These are 2 different approaches, Eulerian and Lagrangian, for the movement that I was mentioning. Okay, thank you. Write it down, because these things comes to the mind and I tell you guys, but it's very difficult to find all this information in one place, one book. I should have written it here, but somehow I skipped.
Like in classical mechanics, we
Correct.
cost functional.
Correct.
So there is method to calculate.
This is where it is taken from in mathematics.
Okay, and here we include mechanics. We
Correct.
do approaches.
Correct. Exactly. That is where it is coming from physics.
Yeah.
Yeah.
So we are borrowing, mathematicians are borrowing techniques from other areas, and it happens all the time, right? But okay. Anyway, so I think I have spent a lot of time in that. I think when I start some things, I start very simple. That's my goal, because there's multiple layers of difficulty. One is the difficulty is to understand disease. Another thing is what data is there, I don't know. So I have to collect the data. And third is mathematical challenge. If I start with a very complex model, I would not know exactly. So if I lump all these difficulty together, I will have multitudes of difficulties. I need to separate it out. So start simple model for the disease in hand and focus on understanding biology first and so on and so forth. Okay, so having said that, I'll stop here. And these are just work for you guys if you want to. I had few slides on, oh my god, this is fine. I have not even, so this is stochastic process, stochastic model, which is also, can I show you very quickly something?
Yeah, sure.
So a stochastic model has an extra dimension. What is that extra dimension? What is stochastic process means? Who can tell me what is stochastic process means? In a simple way, I don't want a book language. I know the book language. So what is stochastic process means? Have you all heard about stochastic process?
Yes.
Yeah. Okay. Stochastic means?
Basically, random
Randomness. What is process means?
process.
If I combine a stochastic process, what does that mean? Process is an important word.
Random phenomena.
No, random. Yeah, it has to do with random, but tell me exactly what is it? So, okay, since the time is limited, stochastic process means is a collection of random variables, a basket full of random variables, right? Random variable, what is random variable?
Which assigns the value to the sample space.
This is a book. Simple. Random variable has a distribution. It is not a single value. It's a group of value with a probability attached to it.
Yeah.
Right? So it's a distribution, and a random variable is that, right? And if you have a random variable here, 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 this collection is called as a stochastic process. So if you are having SIR model like this, it's a mean value, simple mean value. And if you have a distribution at every time, right, that is a stochastic process. This envelope of distribution and the shape of this distribution are also changing. It's not the same. That's what a stochastic process solution looks like. Okay, so the collection is indexed by time. At each time you have one random variable. Each time you have another different random variable. Does that make sense? So that is what I am showing here. You see, this is SIR type model, and this is a sample path. One sample path, second the color coding. But this is actually, think about distribution coming out of this thing at each time. At each time. And that's the process. That's a collection of random variables in the process. Okay. And you know, the goal here is, by the way, if I make deterministic model is stochastic, let's say SIR model is stochastic, what is the eventual solution for that? SIR model is stochastic, this model that we did a simulation on. If I make it is stochastic, what will happen to the solution? Because, see, for example, endemic model, the model just we saw, there were two states, 0, state, and there was an endemic state, right? If I make that model stochastic, that means I introduce stochasticity somehow. I'll tell you how to introduce, but somehow if I introduce, what is the solution will look like? Will you have an endemic state? Its final result always, because of the time, I'm not asking you question, the final result will be always absorbing state. That means 0, state. Eventually the infection will die. There won't be any endemic state. There will be temporary states, but because of the randomness, it will go to 0 eventually. Okay, so there is one absorbing state for model like SIR, simple SIR model, right? And you know, yeah, one thing I want to talk about is this slide, and then I will end, because this will give you a good picture about stochastic model. Now, stochastic models, there are three types of noises in stochasticity. One noise is, again, the source of uncertainty, right? One noise is called observation noise. That means when you measure the data, whosoever measured it made an error. What is that error? I want to capture it in the model, right? Like for example, empirical scientists or ASHA workers noting down and they made an error. And so that's an error. That is called as an observation error, noise. Okay, that's in the data. Then there is environmental noise and demographic noise. You know, have you seen that there are news many times that in some years there is a very good crops, you know, a lot of fruits of certain type, and some years it's a bad crop.
True.
So that's an environmental impact, right? And disease also have an impact like that, because if you are talking about vector-borne diseases, it has mosquito dependent, and environment will play a very significant role in that. Some years there will be lots of mosquitoes. Some years there will be less density of the mosquitoes. It will not be, in fact there will be a significant difference from some years to some years, right? So in that case you are capturing the environmental noise in the model. And what is a demographic noise? What is the demographic noise?
Individual.
Say it again?
Individual.
What is issue?
It's a text I feel.
Yeah, it's written there. But what is it? So, for example, fishes. Not all fishes lay eggs, same number of eggs. Some will lay few eggs, some will lay very high number of eggs. Right? So, that's an individual variability. And this, some species have quite a lot variation in this. In that case, if you are interested, your research question is about that variability, then you will capture that thing using demographic stochasticity. And the way you capture it, also it results in a different analysis, different types of analysis. But these are the two ways we build. This is this goes in the data, but these two are the way you built it in the model. I don't know if you have. So this is demographic stochasticity. It's a linear model, Poisson model, but this is because of Poisson. This is a distribution basically, and the mean is dependent on xt. But since this is a Poisson, therefore it is impacting the number of people, increase in number of people per person, how many they are producing, and so this is demographic stochasticity. This is environmental stochasticity model where it's saying 0.9 that's Hampo in a bad year, and lambda has a value 0.9 in a bad year, in a good year it's 1.1, so this is an environmental stochasticity. But anyway, there's a lot of these things, and the goal of our, it's 5 minutes left now. The goal of this course was to expose you with the many things, not to force you guys to work on certain things. You might have gone through the different coursework, different workshop that teaches you bifurcation analysis. That is not. I know that you will all be learning some bifurcation in some class. So why should I do it here?
Yes.
There's no point in that. I wanted you to brainwash you with a different sense of, again, it's in a good way, not in a bad way. So, yeah. So to brainwash you in a way that you can start thinking it in a broader. Don't, when you go back, don't get absorbed in the same environment of thinking. Okay. So again, you are always welcome to interact with me. I'm a very open person in terms of responding, although I might delay in response. That's a different issue because I'm very busy. But I will be happy to help you all with anything from professionally. Okay. So having said that, I still have to complete some things, but I will not do it today. I think we are all tired. And tomorrow we will start with a panel discussion. This is also very interesting. I could have been a panelist, but I choose to select few people, and I've been forcing them to come. Finally they agreed. So tomorrow we are planned to have a panel discussion first thing. Don't be late, and tell your friends also. Then 9 AM we will start because they are joining it from Canada, US, and one person from Canada, US, 2 US and 1 Canada, and Dr. Tripathi. And think about some questions for them. If you have any questions for them, it will be 1 hour panel discussion. I will be moderating the session, and I will ask them some relevant questions that will be useful for you all also. And then at the end, probably 15-20 minutes, we will open the floor, and you guys are okay to ask them questions. Okay, so that's the plan. And then also Sheetan will be talking about his amazing work. I think I loved when he talked about electronic medical records, health records that he's using, and you know, he's generating models from the data. Usually we don't do it because we don't have the data. He has somehow, his research group has the data, so he's generating these models, scratch from the models. I mean, this data models is from the first step. He's building it from the data, and he's using what, electronic health records, and what is he using for network? All the same thing?
Yeah.
Same data?
Yeah.
Okay. So he's using electronic health records. So we will know 2 things here: how to construct from the data model, And also, what is electronic health record? It's one type of data, real world data. I don't think any one of you have used it. He's using directly from the hospital. If you would have used it in the past, you would have used it aggregated data from the published study. He's using from the hospital, right?
Yes, sir.
He's using directly from the hospital. So it will be amazing to hear it out, what he has to say, and I hope it is useful for you all. So, thank you very much. Have a wonderful evening.
AI models compare to
हाँ वो मैं अभी भूल जा रहा हूँ एक्चुअली काफ़ी कुछ चीज़ें आ जा रही हैं नहीं हम सारी हाँ this is he made a very good point. So what I am doing right now, I am putting on the Google Classroom day by day everything, and all the lectures are there and the exercises that we did are there. It is for you to use, and you know, and is that what you